deep breath. It's okay. The good news is we're only talking about first order kinetics here. So no zero order, no second order, just the one, okay? So radioactivity is natural. It's part of our environment. All of the elements with more than 83 protons and some that are smaller are unstable and undergo radioactive decay. The reason that all of the radioactive nuclides have not just decayed, I mean, the Earth is rather old, right? Is that new ones are constantly being formed, and some of the existing ones decay very slowly, like mind-bogglingly slowly, right? Like millions of years for a half-life. All radioactive nuclei decay via first-order kinetics. So that means that the rate of decay is equal to a constant times the number of nuclei present. So the rate is proportional to how many nuclei you have. The rate constants vary. Some are large and some are small. Half-life means the same thing here as it did in chapter 15. It's the time for half of the substance to react, or in this case, decay. So you've got, if you have 1 gram of the parent nuclide, after one half-life, you'll have half a gram of the parent nuclide. And then after another half-life, the half gram goes in half to 0.25. So this is the relationship between half-life and the rate constant. So T1 half is 0.693 over K. So if the nuclide decays very quickly, it's going to have a short half-life. The rate constant is large. Nuclides that decay slowly have long half-lives. Thorium-232 has a half-life of 14 billion years, right? So pretty sure that not all the thorium-232 that was here, however and whenever things started, has decayed, right? 14 billion years. This is important. A radioactive sample does not decay to 0 atoms in 2 half-lives. You can kind of see how you might think that, right? Well, half of it went in this time, the other half goes. No, because the rate depends on how much there is. So as it decays, the rate slows down. Then we have things like radon-220, which has a half-life of 1 minute. This is the stuff that can be in your basement. We don't have to worry about that because we don't have basements around here. But starting with 1 million thorium-232 atoms, we'd get down to 250,000 of them after 14 billion years. 28 billion years, and it would take 2 minutes for radon-220 to do that.
Yeah, why are they the same?
Because each of these is a half-life. So what's different is the amount of time. So this one decays by half in 1 minute, and this one takes 14 billion years.
Oh, I thought we were saying that from this half it's 1 minute, and then because there's less, then the second half-life would take a different time.
No, the half-life is constant for first order kinetics. It changed for 0 and second order, but it's constant here because the rate depends directly on the number of nuclides that you have. Yes.
Do you know why this decay is, or why the half-life decay is, why the rate is determined by the number of?
Yes, because each nuclide has a certain chance of decaying at any given moment. And so the more of them that you have, the greater the chance that one of them will decay.
Okay, so it's just a probability.
Yeah, it's just, the more things you have, the more decay events you're going to have. Yeah. It's also very convenient. So this is a graph looking at number of atoms of radon-220 over time, and starting out with 1 million. We get this curve, which should look familiar. That's a first order kinetics curve of light concentration versus time, right? You may run into some homework problems that ask you to do things with half-lives and don't actually tell you what the half-life is. And so you might need to look things up here. This also tells you what type of decay these different things undergo. So there's thorium with the 14 billion years. That's thorium-232. And thorium-219 is what? 1 microsecond for the half-life. So, I mean, it's all over the place. So the integrated rate law gives us the concentration of reactant as a function of time. So the natural log of the concentration at time t divided by the initial concentration was equal to negative rate constant times time. So we're not looking at molarity here. We're looking at number of nuclei. So it's still a first order, but now we're going to call it n sub t and n sub 0. So n sub t is the number of nuclei at time t, n sub 0 is the number of nuclei at time 0. Okay. Plutonium-236 is an alpha emitter with a half-life of 2.86 years. How long will it take for 1.3 milligram sample of plutonium-236 to decay to 0.1 milligrams?